Hi everybody, so we are about to begin the unit Astrophysics, and this is unit D1, which is stellar quantities. So stellar quantities. Okay, now this has certain subdivisions. So in this unit we are going to see certain things. One is objects in our universe. Objects in our universe. We are also going to see nature of stars. Then we are going to study astronomical distances. Okay. Then we are going to further see what is our understanding of stellar parallax. And something that we have already studied earlier in the energy unit, unit 8, that is luminosity and apparent brightness. Apparent brightness. Okay, so let us begin now. So we would like to begin here with objects in our universe. So if you think of all the objects that are in our universe, what are they now? In our universe, we have stars, we have planets, we have asteroids, we have constellations, we have nebulae, so many aspects. So one by one we will just briefly write about it. The first thing that we are going to write is solar system. So, when the Big Bang happened, Big Bang happened. After Big Bang, we started getting all the fundamental particles, which you remember in the unit 7 we did, fundamental particles. And after that, we started getting the formation of the stars, planets, and then we started getting some specific format where planets, due to gravity, were moving around star. And one such example of this is our sun. And we have planets moving around sun. Okay. Now, this setup where you have planets moving around sun, this setup or this system is called solar system. Solar system, right? With sun. Solar means it represents here sun. So we have a solar system. Now, what do these solar systems actually have? These solar systems also have moons, They also have asteroids, which we will discuss after some time. They also have comets, and they also have some rocky substance. Okay, we will come to each one of them one by one here. So let's begin. First, what do we understand by asteroids? You know, these asteroids technically have irregular shapes. Irregular shapes. What do we mean by irregular shapes? It simply means it can be something like this. Now, what do these asteroids actually consist of? So they consist of technically the dust, some gas, and they move sometimes in some pattern. So they move in some pattern. These patterns are called your asteroid belt. Okay. These are found mainly between Mars and Jupiter. So they are found between Mars and Jupiter. Right? So what are asteroids? Asteroids are irregular shapes. Irregular shapes, and irregular shapes of asteroids, they consist of dust, gas, and they move in some pattern which are called asteroid belt, and they are found between Mars and Jupiter, especially in our solar system we are talking, right? Their size is something approximately like, say, 300 kilometer, something that order. Now, coming to the next aspect. Next one is very important for us, and that is stars. So technically, what is a star now, right? So star, we know, consists of hydrogen, and these hydrogen undergo fusion reaction, and because of the fusion reaction, the hydrogen combine to form heavier nuclei. Heavier spelling is nuclei. Check the spelling. Heavier nuclei. Now, what exactly happens in a star now? In star, two things happen. One is you have an inward pull, which is due to gravity. Okay, due to gravity. You also have at the same time an outward push here like this. Okay, in all directions. These are because of the nuclear reaction. Nuclear reaction. Now the question is here, how is a star formed? Okay. Technically, a star is formed from what we know as nebulae. Now, you know, when Big Bang happened, when Big Bang happened, these nebulae were formed. This always has a cloud of dust and gas. Now, what exactly happens is, if you have an outward and inward, and if there is a balance here, there is a balance here which is known as hydrostatic equilibrium. Hydrostatic equilibrium. Okay. Yeah. This is a very important key here. You must know this one. So it's a hydrostatic equilibrium. Remember this term. This is a very important term for us. So a star consists of hydrogen, undergoes fusion, hydrogens combine to form heavier nuclei. Now, when a fusion reaction is going on, there are always two forces acting here. One is due to gravity, it is pulled inward, and due to the nuclear reaction, the thermonuclear reaction, it is pushed outward. Thermo is also a good term here. And this is balanced here, which is called a hydrostatic equilibrium, because they both are brought into an equilibrium. Okay. Now, when this happens, a star is born. And this small star, the young star, is called protostar. Okay. So how is a star formed? It is formed from nebulae. And when did nebula form? It formed when there was a Big Bang. And after the Big Bang, the nebula came into existence. After billions of years, of course. And what is nebula? Nebula was formed as a cloud of dust and gas. And then there was a gravity effect here. Because of the gravity effect, all these particles, they came closer, you know. So we can ask a question here actually. Question can be, why? The question you can raise here is, why did temperature of star increase? You know, and that answer can be given as something like this. So, as gravity pulled objects closer, by objects here you mean hydrogen and other, okay? Hydrogen or helium, all those stuff. Closer, the potential energy decreased, and kinetic energy increased. Hence, the temperature also increased. Okay, that's how the temperature of a star increased. So it was both the gravity, the main factor was the gravity, which pulled everything closer, so the potential energy decreased and kinetic energy increased. And we know that if kinetic energy increases, what happens? The temperature also increases. That's a funda actually there. Okay. Now, This is about star that we just now saw. Let us go to something else which is also called, we also observe some characteristics in the way stars are placed, or you can say they position themselves. So what is exactly this now? We have to understand. So one of them is called your binary star. Binary star. And binary star is nothing but there are two stars which remain together in a specific manner. What is the specific manner now? There are two aspects of this. One can be these two stars, they move, one is here, star, and one is here, okay? So this is star A, and this is star B. So if you look here in this case, what exactly is happening here is both move in fixed orbit, but their radius is different. Okay. Another way the binary star can be formed is that there can be two actually here. There can be two here. So one can be here and one can be here. So it can be star A and this can be again star B, right? This also can happen. So single orbit. Now in both of these cases, what actually happens? In both these cases, if you observe, the stars can remain at two different positions like this, or they can also come like this. So there can also be a position where you can have a star here and then you can also have a star here. You see? So in this case, what happens now? Your intensity will become less because you are going to receive intensity only from one star. You can't see the next star. So there are variation in intensity, and we can use these properties to study their mass. Okay. So the way these stars actually remain, we can study their mass, we can study their, property, how much, what is the fusion rate at the moment going on inside them. There are so many properties one can study about these stars. Okay. Next, we have something called constellation, under group of star. We are still doing under group of star. Let us name this as something like say A. Okay. And then we will do now B. So B will be constellation. Okay, this is just like so constellations are also group of stars which remain in particular pattern. Now these patterns are actually used by astronomers also. Use these patterns to make predictions. Okay. And the last one we have, not in this group, but the last aspect of this is what is in our universe, objects in the universe. We have galaxy, and galaxy we know very well now because we are in the Milky Way galaxy. Our galaxy is Milky Way, and it is a spiral galaxy. Its shape is actually spiral. And it always consists of all the stars, billions of stars, and solar system, and so many other astronomical objects. This is how the shape looks like, and we might be somewhere here. Okay, this is our position. You can do further research on this. You can also do some further research. Okay. Now, before we go into the next topic, I would like to put a question for you. Just think about this question. What could be the possible answer? So, think. How are planets different from stars? And are there similarities between planet and star? Now just think about this. So with this we are going to end the first aspect of this topic, chapter D1. Now we are going to get inside the next topic, which is called your astronomical distance. Okay, astronomical distance. Okay, so let us discuss this now. There are so many distances that are used here. These are specific unit used to measure the distance in astrophysics. And what are they now? One can be the average solar distance. That means the distance of sun from earth, but average. Why are we taking average? We take average because the path of the sun is not, the path of the earth is not fixed. You see, this is sun and earth is here, then earth is here, then earth is here. So the distance of the earth keeps changing, right? So you find the average distance here. Okay. And that average distance is known as your astronomical unit. Which is 1 AU, and that is equal to 1.5 into 10 power 11 meter, which is given in data booklet. Okay. Second one is light year. This is the distance traveled by light in 1 year. Okay. So this value is approximately 9.46 into 10 power 15 meter. Okay. So if needed, we have to use this. You can calculate this actually. You can calculate this because speed is distance by time. So distance is speed into time. Speed of the light is 3 into 10 power 8 into time is 365 into 24 into 3600, and then you should be able to get it. As simple as that. Okay. Third one. Parsec. This is also unit for length. Unit for length or distance. Okay. Sometimes we need bigger units. Bigger units. As distance is very far. Is very far. So 1 parsec PC is equal to 3.26 light year. Okay. So light year is technically LY. Anyway, these are all given in data booklet, so you don't have to by heart them. You have to just understand what each one of them means. Okay. Right. Now we are going to have a look at something new concept that is called stellar parallax. So what is stellar parallax now? It's a method used to determine distance of stars from Earth. So we use some sort of, we take help of trigonometry in mathematics. So we use simple trigonometry because we know that sine theta is equal to opposite by hypotenuse. Now let's say a situation where we have the position of our Earth moving around Sun as like this. Let us say we have the Sun at the center. This is going to be our Sun. Okay, so this is going to be Sun, and then we are going to have the star somewhere here. Okay, and we are going to measure the star from two different points here. So here, let's draw this also. This is your one astronomical unit, let us say, average distance of Earth. This is your Earth. Okay, this is your Earth. So in a term of time of 6 months, you are from here to here, and you measure an angle which is theta. Okay. Now this angle is called your, this much angle is called your parallax error or parallax angle. Okay. Parallax angle. This much. Okay. Now this parallax angle they are showing by P, and this distance is D. So we very well know that sine P then would be opposite, which is your here to here also is 1 AU, right? So it will be 1 AU by D, the hypotenuse. For smaller angles, sine theta can be taken as theta. Therefore, we can write P equal to 1 by D. We wrote that 1 here because we know that 1 is nothing but 1 AU, right? This is the angle, and it is measured in unit called arcsec. Okay, 1 arcsec, and this is the distance in parsec, and this is your 1 astronomical unit understanding, average distance of Earth. So if somebody will ask us, define 1 arcsec, how do we define now? So we can define it as, it is the angle subtended by a star at a distance of 1 parsec. Okay, that's understanding. Now let us go to the next concept that we have. So the next concept here is, we are going to understand is, what is luminosity? Okay, so what is luminosity? Let's understand. You know, from any star, two things happen. One is the star radiates, and we receive, right? There are two things here, see, star radiates and we receive. So technically the power of radiation from star is luminosity. Okay, and power received per unit area is known as apparent brightness. So how do we now write apparent brightness? Apparent brightness one second. So apparent brightness is B, which is defined as L by 4 pi d square. Okay, what exactly is this D now? This D is the distance. So of position from where we watch star. Okay, now technically we know light from star will spread as a three-dimensional, like a sphere. Okay, and because it is a sphere, we use area 4 pi r square, but r is the radius and the distance, so we write it as 4 pi d square. Let us just visualize here. I will try to put some image here. So this is this is, and this is the star. Okay, this is the star. So if I watch from here, then this is my radius, which is equal to d, so r1 d1. If I watch from here, then this is my radius r1 and r2 and d2, r2 and or d2. Okay, because his area will be 4 pi r2 square or 4 pi d2 square, like that. Okay, so it depends on where you are watching the star from, that distance. So radius and distance are same here. So radius and distance both are same here. So now I think the apparent brightness is clear. So technically, for example, if we receive from sun on earth 700 watt per meter square, then it means luminosity or the power of radiation is 700 watt, and we are receiving it per unit area. Okay, now we come towards the last part of D1, which is your black body radiation. So let us try to understand this now. So black body radiation. Technically we know that black body does not reflect. But it can emit radiation, right? This is a technical understanding of black body. Now stars also have similar properties. See, what is the property? The property is that it also emits radiation. And because it emits radiation, so we treat them as black body. And that's the reason why the power of stars can also be written as sigma A T power 4. This we have already done in the unit of unit 8 we did. So you can recall from unit 8. Okay, where your A is the area of star, and because it is spherical, considered as spherical, not spherical but considered, so we use 4 pi r square, where r is the radius of star. Okay, and the unit of this is of course watts. This particular thing is known as your Stephen-Boltzmann constant. Sorry, one second. I'll just erase that. It just came from. Okay, so Stephen-Boltzmann constant. It's a constant, and its value is given as 5.67 into 10 power minus 8 watt per meter square per Kelvin power minus 4. So this was completely about your unit D1. Okay, I hope it is now clear. and you should be having no problem now. Okay, so we began with all the 4. We have discussed all these 1 2 3 5 we have discussed, and if there are any further doubts you can ask, and I think we are done with all the aspects of this till here. Okay.